Leah here from Leah4sci.com, and in this video I will show you how to analyze between a nucleophile and a base in substitution and elimination reactions. Since nucleophiles and bases are the key players in substitution and elimination reactions, let's start by identifying and understanding the nature of each molecule. If we break down the word nucleophile, we have nucleo, which sounds like nucleus, and phile, which means loving. And since the nucleus is positive, a nucleophile is a molecule that is positive seeking and therefore will have to be negative or partially negative. We can define a base using three different definitions. An Arrhenius base is a molecule that will break down in water to give you an OH-. A Bronsted-Lowry base is a molecule that accepts an H+ regardless of the solution. And finally, we have a Lewis base, which is an electron pair donor. In my videos, I will represent a nucleophile as Nu with 2 electrons, reminding me that it has those 2 electrons it can attack with, and the base I will show as a B for base, again with 2 electrons to attack. If we analyze the different definitions of a base, OH- is negative, a molecule that accepts an H+ is going to be negative or partially negative, and a molecule that has an electron pair to donate, again, will be negative or partially negative. So the only thing we've proven with these definitions is that a nucleophile and a base can actually be the same exact molecule, and let's show this in an example. Here we have 2 reactions that both involve a 2-bromobutane being attacked by an OH-. Bromine as a halogen is partially negative and will pull electronegativity from the carbon, leaving that partially positive. When the OH- reaches out with its electrons to attack the partially positive carbon, thus kicking bromine off of the molecule, this by definition is nucleophilic substitution, making the OH- in the first example a nucleophile. However, let's not forget that when bromine pulls electronegativity from carbon, leaving it partially positive, some electronegativity is also pulled from the bond between the beta carbon and the beta hydrogen, leaving these hydrogens partially positive. If the OH- chooses to grab a hydrogen instead of attacking the carbon, this will cause the bond between hydrogen and carbon to collapse towards the leaving group, kicking out bromine and giving me a pi bond in my product, along with OH- now bound to that beta hydrogen. Since OH- grabs a hydrogen from the molecule, in this scenario, it's actually acting as a base. So how do you tell the difference between a nucleophile and a base? 3 things you want to keep in mind. The first is that you will usually have competing reactions between substitution and elimination. The second thing to keep in mind is that some nucleophiles will be pretty poor bases, and some bases are going to make poor nucleophiles. And the third thing to keep in mind is that you cannot look at just the attacking molecule to determine if it's a nucleophile or base, but you will also have to look at outside factors, including the carbon holding the leaving group, the potential to form a carbocation, and the solvent that the reaction takes place in. So while it's difficult to distinguish, knowing that there are competing reactions, it's easier to first look at your molecule and determine if it will undergo a 2-type reaction, such as SN2 and E2, or a 1-type reaction, such as SN1 and E1. Picture this scenario. You have 2 little boys on a playground that want to play on a swing. One is a shy little kid, and the other one is a big, strong bully. If the shy little kid manages to get to the swing first, but the bully decides that he wants the swing, he has one of 2 options. He can either push the little kid off the swing, or he can simply yank the swing out from under the little kid. In both scenarios, the bully winds up getting the swing. Now the other little kid, shy of running to his mother and crying for the swing, will only have one option, and that is to wait and wait and wait until the bully decides he's done with the swing and vacates, leaving an open swing and therefore an opportunity for the little kid to come in and grab it. This is exactly how I want you to think of the 1 and the 2-type reactions. A 1-type reaction takes place with a carbocation intermediate. That means you have a weak nucleophile or a weak base, which is like your shy little kid that does not have enough strength to attack and kick a molecule out. Instead, it has to wait and wait and wait for that carbocation to form, which is a slow reaction. But once that positive charge is there, the weak nucleophile or base seizes the opportunity and attacks at that open charge. The 2-type reactions, on the other hand, occur when a strong base or a strong nucleophile attacks a molecule like a bully. So even if you have the opportunity to form a carbocation, that is way too slow, and this strong bully of a molecule does not want to wait around. So when you have a strong molecule, it will simply attack the molecule, kicking out the leaving group to ensure that the reaction happens at the speed preferred by the bully. So how do you determine if the incoming molecule is strong or weak? There are three things you want to look at, the first of which is charge. Remember, these attacks happen when you have a partial positive carbon or partial positive hydrogen attracting a molecule for attack. Therefore, the more negative your attacking molecule, the more likely it is to attack, the stronger the reactant, and therefore the faster the reaction. Let's take a look at oxygen. Oxygen is a highly electronegative atom and can be found bound to many different groups, for example, hydrogens or carbons. When oxygen is bound to just one atom, having 3 lone pairs and a negative charge, that oxygen is considered very strong and will prefer a 2-type reaction. While the water molecule is neutral, the oxygen is still considered partially negative due to the polarity and can still attack as a base or a nucleophile, but this is more likely going to occur as a 1-type reaction because water is not strong enough to kick out a leaving group. And finally, we have hydronium, where oxygen has too many bonds and a positive charge. Hydronium will be repelled by the partially positive carbon or hydrogen and therefore does not participate as an attacker in substitution or elimination. You can apply this trend to any atom that has the potential for attack. A negative nitrogen is very reactive and will be a strong base or nucleophile. A neutral and partially negative nitrogen will be a weaker base or nucleophile, and the positive nitrogen will not attack at all. How does this apply to the 1-type or the 2-type reactions? If you see a reacting molecule, such as CH3O-, recognize that O- is going to be a strong base or nucleophile, giving you a 2-type reaction. But if you see a molecule like CH3OH, recognize that this is weak and this will give you a 1-type reaction. But now what happens when you see the molecule NaOCH3? This is a very common occurrence, but don't let this trick you. The actual molecule reacting here is not NaOCH3, but rather CH3O-. Anytime you see a group 1 element at the start or end of your molecule, this is simply a spectator ion here to balance your charge. What you have is a positive sodium balancing the charge of a negative CH3O-, which once again is a very strong base or nucleophile. You may also see potassium or lithium as a spectator ion, and when you do, simply cancel it out and simply give a negative charge to the molecule that follows. Are you struggling with organic chemistry? Are you looking for information to guide you through the course and help you succeed? If so, download my ebook, 10 Secrets to Acing Organic Chemistry, using the link below, or visit Leah4sci.com/orgo-secrets. That's ORGO secrets. If you enjoyed this video, please give it a thumbs up and even share it with a friend or two. If you have any questions regarding this video, leave a comment below or contact me through my Facebook page at facebook.com/Leah4sci. There will be many related videos posted over the course of the semester, so go ahead and click the subscribe button to ensure that you don't miss out.